Okay, so starting out here, what is a chemical reaction? Well, a chemical reaction is where we have chemical bonds that are broken in something and then reformed in a different way. We always write our reactants, the things that are going into our reaction, on the left side of an arrow. We don't use an equal sign. I know some of you are tempted to use an equal sign. This side is equal to that side, which basically it is. But we're saying that the reactants are forming the product, so we do an arrow from the left side to the right side. If you're in DECA, that sort of thing, you can think of products as the things you're forming, those things that you're going to end up selling. Those are your products. And it's also like a recipe. You take the ingredients, those are your reactants, put them all together in the special ways that you need to, and you get a delicious treat like chocolate chip cookies as your product at the end. So conservation of mass. Chemical reactions always conserve mass. We're not creating matter out of nothing. We're not destroying matter. The mass of the reactants have to equal the mass of the products. The equations have to be balanced to satisfy this conservation of mass. And since we're not dealing with nuclear chemistry here, whatever our reactants are, those same chemicals have to be on the product side. We can't take hydrogen and oxygen and then on the product side have magnesium and oxygen. It's not working that way. If we were doing nuclear chemistry and actually changing the protons, we could theoretically be changing that sort of thing, but we're dealing with regular chemical reactions here. So we're going to have the same reactants and products, the same chemicals on both sides, just rearranged in different ways. So when we're balancing an equation, we have to write it out first in the formulas, or the symbols. That's what we were doing last week. We were writing out the symbols from the names. And that's going to show up on your test. We use coefficients in the front of the chemicals, so we use a big number in the front of the compound to change the quantity or the number of moles of that chemical. We are never, ever, ever going to change the subscripts that are used in the formulas, because that's going to change the chemical itself. So the coefficients, the number in front, tells us the number of molecules, and the subscripts, the little bottom numbers that we get from either crisscrossing or looking at the name, tell the number of atoms in the molecule. It should be LE at the end of that. Yeah. Still see quite a number of pens going. Get that finished up so we can move on, please. Okay, that's most of them. So, here's our first example. If I have hydrogen gas and oxygen gas and I react them together, now it's going to take some sort of energy to make this happen. We don't write the energy out though as being added into it, but we need something like heat to make it happen. Or maybe I need ultraviolet light. Bless you. I would write these sorts of things that are not actually reacting, but that are helping the reaction occur just above the arrow. Why is this H2 and O2? Yeah, when it's by itself, it's always diatomic. Diatomic molecules. Okay, they're only stable if they're with another one of themselves. So if this was written out, hydrogen and oxygen gases react, you would have to remember, oh yeah, hydrogen and oxygen are both diatomic, so I have to write them out as H2 and O2. Form dihydrogen monoxide as a liquid. Sometimes it's gaseous and then it goes to a liquid. So this G stands for gas, L stands for liquid. We can have an S that stands for solid, and we can also have AQ that stands for aqueous, which means dissolved in water. If you're given something in words and it's being descriptive, like it's saying hydrogen and oxygen gases, then make sure that you're writing down the G in parentheses behind that. Now these G's are not something that we have to balance out. It's just telling us more information about how this reaction is occurring. And we saw this reaction last week in that big packet that we had. And some of you were like, wait, they don't match up. Two sides don't match up. Some of you are already thinking about that conservation of matter. So, you're right, they don't match up. We're going to need to balance it. Can I just put a 2 there? No, why? Yeah, then it's hydrogen peroxide, which is not something I want to drink. We simply can't add the 2 to the water because that changes the chemical itself to hydrogen peroxide. So that's a no-no for us. What we will do is change the coefficients. So I'm going to put a 2 in front of the water, which changes the whole water molecule to 2 moles of water. So now I have 2 oxygens on the reactant side and the product side. But what did I do to my hydrogen in the process? I doubled it, yeah, so now I have 4, yep. I have 4 hydrogens now on my product side. I need 4 on my reactant side. So what should I put my coefficient as? 2, absolutely. So we simply have to add a 2 in front of the H2 to make that equal on both sides. Now we're just going to go through a few examples of balancing today because some of you are going to get it right away. Some of you are like, oh yeah, done that before, no problem. Some of you are going to struggle a little bit more. And what I recommend for you, since we don't have an official homework assignment tonight, is go online, type in balancing equations. There's going to be lots of modules on there that you can do lots of different examples. So if after we're done today you're like, I don't quite get it, just go ahead and do that. Okay. We're going to do a reaction that you've seen. So we did it in the lab the other day. But we're going to do it so it's not captive in a teeny tiny crucible. So I've got magnesium here. What are some of the things that you saw that indicated that a chemical reaction occurred? It turned to ash, absolutely. So my new compound was very different from the properties of this metal that I'm starting with. The metal is malleable, I'm twisting it, I'm turning it, I'm having fun with it, I'm making a little curly Q out of it. The ash that I got would break up. Yeah, it changed color. So sometimes color change is a very, very, very good indicator for us. If you were like taking food dye and adding it to water, that's not a chemical reaction. But I started with silver and a colorless gas, and I got a whole new color. I got white, which was an indicator that if I get a whole new color, I've got a whole different compound. What other things did you see that would indicate color reaction? Smoke, yes. So we had some gas, perhaps, that was being formed as a byproduct. It was not a complete reaction. Yeah. Yes. So we wouldn't actually be touching it, but we would see a temperature change in it. Yep, it's very exothermic. Well, it's kind of going from a solid to a solid. We're going to see more where it would be that later. The mass did change because I added oxygen to the system, because we couldn't figure out the mass of that oxygen to start with. Good. I'm going to put it in some flame here, and I want you to not look directly at it while it's going. Natalie, would you turn the lights off for us again, please? Yeah, don't look directly at it. Yeah, I dropped some of the copper on it last week, or 2 weeks ago, whenever that was. Okay. Then you're going to want to make sure to not look directly at it. That's why. So, what's the other thing that's happening here? Why am I not looking at it? Because it's producing light. This reaction is giving off light. Yeah, I took it out of the flame. It wasn't the flame that was causing it. The flame catalyzed the reaction. The magnesium wasn't reacting with the oxygen in the air. Go ahead, Natalie, thank you. Just naturally. So we saw light being produced, which is another indicator of a chemical reaction. So let's unmute this. And this one's not on your sheet, but if you can find a little spot to write something, that would be awesome. Okay. So the magnesium, what's the symbol for magnesium? Mg. Is it diatomic? No, it's not. What state was it in to start with? Solid, good. And it reacted with what? Oxygen, absolutely. Is that diatomic? Yes, so O2. What state was that in? Gas, yes. I think I did a little bit too much for you guys. It's hazy in the room now, that's not good. So, it formed magnesium oxide, which hopefully your empirical formula showed that if we have Mg2 plus O2 minus and we crisscross those, we get MgO. What state was that in? Yeah, solid. It's on the table right there. It's a solid. So, this needs to get balanced. I want you to try it on your sheet there. So, is there going to be a coefficient in front of the magnesium? Yes, what will that coefficient be? 2, absolutely. Is there going to be a coefficient in front of the oxygen? No. What about in front of the magnesium oxide? Yes, what will that be? 2. Now I've got a balanced reaction. So if I were to do this in words, it would be something like 2 moles of magnesium solid, or metallic magnesium would be another way to say that, react with 1 mole of oxygen gas to form 2 moles of solid magnesium oxide. You're going to be able to, by the end of this, transfer those words into these symbols and balance it out. Questions so far? Yeah.
So 1 mole of oxygen is actually like 2.
Yes, there are 2 atoms of oxygen in 1 molecule of oxygen gas. Okay, I have another one for you to try, I believe, or some more hints. Okay, good. Another one for you to try. Try this on your piece of paper. Some people will find, as you're starting this out, until you've got the hang of it, that you can kind of do it as an accountant would. So you want both sides to equal, like you want your bank statement to equal what it says in your checkbook. So if I imagine that as my dividing line, I can say, well, I have aluminum, magnesium, and oxide on both sides. I'm going to, write it the same way, Al, Mg, NO on that side. Well, I have 1 aluminum on this side, 2 on that side, 1 magnesium on the reactant side, 1 on the product side, and 1 oxygen on the reactant side versus 3 oxygen on the product side. So I can see that my magnesiums are good to start with, so I don't want to start there. I maybe want to start with my aluminum. So I'm going to say, well, if I have 2 aluminum here, I'm going to put a 2 as a coefficient there. Now I have 2 aluminum on this side. This plus means that that 2 does not get carried over into anything else. Some people think, well, if I put a 2 there, it carries to everything else. The plus or an arrow is a division. Not as in dividing, but it's a division as in it doesn't carry through anymore. Okay, my aluminums are good, my magnesiums are good, my oxygens aren't though. So I need to put a 3 in front of my magnesium oxide, which not only changes my oxygen, but also changes my magnesium to 3. I would never do Mg, a big 3 in front of the O, as well as I would never do MgO3. Those are not things that we can do. We have to do it as a coefficient in front of that whole compound. So I'm almost good. My aluminums are good, my oxygens are good, my magnesiums used to be good, but they're not anymore. If I put a 3 in front of the magnesium there, though, I am good. Yeah.
So it doesn't matter that we only have 3 oxygen?
How do you mean?
Because it has to be 2 oxygen.
Only if it's by itself. So if it was just oxygen on its own, it would have to be 2. Good question. Other questions before we move along to example 3? Yeah. Yeah, so I had 3 oxygens on my product side, and I needed 3 oxygens on my reactant side. The only place that I have an oxygen is in my magnesium oxide compound, so I have to put a 3 as a coefficient in front of that whole thing, which changes my oxygen to what I needed it to be. It also, as a result, changed my magnesium, so I had to write that that changed to a 3. which was an easy fix because on the other side, the product side, I could just put a 3 in front of the magnesium that was on its own, and then it would be balanced. Okay, this next one is a little special for us because we have a polyatomic ion group on both sides. And when it's the same on both sides, we can treat it as the same. Go back. Go back. So I can treat my NO3, since it's NO3 here and NO3 here. I see that I have an Fe, an NO3 group, an Na, and a Cl on both sides. Fe, NO3, Na, Cl. My irons, I have 1, nitrate 3, sodium 1, chlorine 1, iron 1, nitrate 1, sodium 1, chlorine 3. So if I put a 2, or 3, excuse me, in front of my NaCl and NaNO3, that changes my Nas both to 3, my Cls are at both 3, and my nitrates are both at 3. And again, I could do that because they were the same group on each side. You could have also, bless you, done it as Fe, N, and O, Na, and Cl, but it would have probably taken you a few extra steps. So if you start taking apart those polyatomic groups, even though it's the same on both sides, generally takes you more steps. You'll be able to solve it, but it'll take you more steps. So, other helpful notation, we started talking about this a little bit. If you write something above an arrow, that's just helpful information for you. So if I have a delta, which is the Greek symbol for D, that means heat change. Or I could write out heat. So I'm adding some heat to it. You might also see an arrow with UV. Maybe we need a special type of light for it to occur. These down here are catalysts. Platinum is a common catalyst. MnO2 is a common catalyst. They don't actually react with the chemicals. So they're not a reactant. They're not shown in the products. They just decrease the activation energy that is required for the reaction to take place. We're going to see if this one will work for us this hour. It did not work last hour. Okay. I've got hydrogen peroxide with some soap in it. I'm going to decompose the hydrogen peroxide into hydrogen and oxygen gases by adding a catalyst to it. My catalyst is potassium iodide. It's kind of a yellowy liquid. The solid thing at the bottom is just a magnetic stir bar. Why is it foamy? The soap, and also what? Soap doesn't just become a foam on its own. Yes. My hydrogen and oxygen gases are making that foam up. Is it the same color it was before? No. So again, we're seeing color change as an indicator of a chemical reaction. We're seeing gas being produced. That's an indicator of a chemical reaction. That's actually one of the driving forces of a chemical reaction. And it's going to react like that for a little while longer. So in this instance, we would write that we had H2O2, which was a liquid, with a catalyst above the arrow of potassium iodide, forming hydrogen gas and oxygen gas. Again, it's H2 and O2 because they're on their own. And this one is already balanced. So I'm going to write out already balanced. That's a good habit to get into. That way, as a teacher, if I'm going through stuff, I can tell that you actually thought about the problem and made sure that you understood it rather than just leaving it blank and being lucky that it was already balanced. Because that happens sometimes. Yeah, Caleb. We're going to talk more about that when we talk about the energy of a reaction and activation energy. I don't want to get into it too much here. Good question. Okay, here's some helpful hints when you are doing balancing, and again, that's all we're going to be doing on balancing as notes. So if you need more help before we do some practice next week, you can, or later this week, you can start working on some of it with your computer. So watch for those polyatomics, make sure they're the same on both sides, and if they are, you can treat them that way. Save balancing hydrogen and oxygen for the end. And use a pencil. It's on there twice because it's very helpful. A lot of erasure marks. Okay, so dealing with reactions. We want to look for evidence of a reaction. Some of those are the color change. We've seen that twice already today. Another one we've seen once before. It's been a while though. I have my special paper. I'm going to hit it with some ammonium. And we get some science being done. We've got a color change there. Visibly see that. Sometimes I can take two liquids and pour them together and all of a sudden I get a solid. That's what a precipitate is. Precipitate is a solid. It precipitates out of the reaction. Yeah.
Is a foam solid or?
It's there's a whole book on foams that's very interesting. It cannot be classified as nice and neatly as we would like it to. Good question. We've seen the gas produced today with the elephant toothpaste. You've seen it before when you've taken baking soda and vinegar and put them together. That's a chemical reaction that's producing a gas. We would be able to, if we could save that gas, show that mass has been conserved. A lot of times people will use that type of reaction to say, well, matter is not conserved. I have a different mass at the beginning and the end. Well, that's because you let all of the gas escape. As long as you're able to keep that gas, you're able to tell that the mass is the same on both. Temperature changes as well. There's two types of temperature changes. We have endothermic which takes in energy, which means it feels cold if you're to touch it. And we have exothermic, which gives off energy, so it's going to feel hot. There's one that's not on here that should be, and the evidence of a chemical change is the formation of light. Which again we saw with the magnesium when we lit it on fire. We got that chemical reaction going to form that magnesium oxide. We formed light. Natalie, do you want to turn the lights off again, please? Okay. Another one that we often see, especially on the 4th of July. I break the glass that's in here so my chemicals that are in here can react. And we get light. We got a color change and light. We don't have any gas or anything like that, but we do have light forming out of seemingly nowhere. And Natalie thinks we have talked about that so much today. Okay. So, one last thing before we can get going for the day, and that's the most common driving forces of a chemical reaction. We've got the formation of a solid. So if I take two liquids and a solid forms out of it, I'm probably going to have a reaction that occurs. And when we deal with solubility, you'll see what types of things that could be. Formation of water. If I take two things and then all of a sudden get water, like an acid and a base, that's going to give me water as one of my products, and that's a common driving force of a chemical reaction. Transferring of electrons. This is a redox reaction. Oxidation and reduction is transferring of electrons. And then also formation of a gas. So if it's likely to form a gas, most likely we will have a chemical reaction. And I've just got a couple of pictures there. Oops. So this one, I've got a yellow precipitate forming. When I take two clear liquids, clear colorless liquids, and put them together, I get a yellow precipitate. The one on the far side is that baking soda and vinegar creating that gas. And that is as far as we're going to get today. We didn't get as far as the other hour, but that's okay. Come ready with your notes. We're going to get started right away again tomorrow. Yeah.
Well, Danielle and I were absent Friday.
Mm-hmm.
Just anything like
Just typing them there.
report.
So, yeah.